Hello all, in this lesson we're going to be studying the introduction to waves, and as you can see it's packed full of good information. Alright, this is the homework associated with the lesson, 1 through 47. We'll work on those in class this week. And our aim is what are waves? Please copy down this do now section and we'll answer those in class. So in essence, a wave is just this vibration that's happening in a medium. And a medium could be air, it could be water. In general, we would probably call it some field of matter. And the wave goes through there and it makes the particles in that medium vibrate around an average position. That vibration is going to match the vibration of the source. So a couple of really common examples are like radio waves that we use to communicate over long distances. And the vibration of the radio wave will match the vibration of the electrons in the transmitter. This is something we learned about in a previous lesson, that charges that are moving can create these electromagnetic fields, which we are now calling waves. Also, you could think of this in terms of a tuning fork. I know my vocal majors and maybe my instrumental majors use these. But a tuning fork, you use it by just sort of taking this hammer down here and hitting one of the arms of the tuning fork, which sets them into a vibration, something like this. The arms of the tuning fork will just sort of vibrate back and forth along those directions, and they will slam into air molecules, causing a wave to move outward from the fork. And so I tried to show that here by putting in these regions of compression where the tuning fork has sort of slammed into the air and made a compressed region, and those will travel away from the fork in what we would call a wave. So in this case, we are going to strike the tuning fork with a hammer to set it in motion, which will make the tongs or the arms vibrate back and forth. Those will rhythmically compress the air around the tongs, and the medium is air. Alright, so let's talk about waves and energy transfer. Basically, you should think about waves as being energy. They don't actually move the matter through space. Instead, the matter, like in the previous example, is vibrating back and forth around an average position, but the wave moves forward. So you could think of it sort of like if you're standing in a crowded room and someone shoves someone on one side of the room, that shove may be transferred from body to body across the whole room, but the bodies don't actually move much. Like, you actually stay basically in the same position even though the shove can actually travel. So this can happen in a vacuum if it's a very specific kind of wave. It has to be an electromagnetic wave. But the waves we were talking about on the previous slide do require media. So just know that there's no actual transfer of mass, and that mechanical waves require media, but electromagnetic waves can travel through a vacuum, which is super awesome. And two examples of electromagnetic waves are radio waves and light waves. So here's a question. If a person screams in space, could she be heard? The answer would be no, because a scream would be a mechanical wave, just like the tuning fork from the previous slide. And mechanical waves need media. Yet there are light waves that travel through space all the way from the sun to Earth constantly, and that's possible because light waves are not mechanical, they are electromagnetic. So quick quiz, wave motion in a medium transfers energy only. While the matter does vibrate a little bit, it's going to be vibrating around a fixed position, and so we would not call that a transfer. So I have a little vocabulary for you. First of all, a pulse is when you just send basically one wave through a rope, and you can see an example of that in this diagram. So there's your definition. A pulse is a single short disturbance that moves from one position to another in a field or medium. All right, but if that pulse reaches a boundary in the medium, something interesting happens. So we have this pulse coming through the rope, and it's going to hit this boundary or an unyielding body. And you have to imagine that when it reaches the wall, it's going to be sort of pulling up on this section of the wall because the pulse is in the up direction. So when it hits the wall, it'll pull up. And by Newton's third law, you know that the wall will have to pull down on the rope with an equal and opposite force. So when the wall or when the pulse bounces off the wall, it will have experienced a pull in the downward direction, and that's why the pulse will be in the downward direction on its way back. So that's called reflection, and of course, you should know about it. It's the rebounding of a pulse as it strikes a barrier, and it typically does reverse the direction. So when I ask you what's the direction of the force exerted by the rope on the wall, conversely, what's the direction of the force exerted by the wall on the rope, we can go with up for the first question and down for the second. Now, there is one more thing in terms of vocab for this slide, which is a periodic wave, and we're going to need to watch this video to understand it fully. So that's a periodic wave, and it's basically a series of regularly timed pulses. It just keeps going and going and going, and it has that really characteristic wave form. I'll play it one more time. So it's a periodic wave. So the two waves forms that I want to talk about on this slide are longitudinal and transverse. A longitudinal wave is one where the wave's vibration and the motion of the wave are parallel to each other. Check out this video. So one thing you might have noticed is that, just like in this diagram, the particles were vibrating back and forth, although not being transferred from one side to the other. And as the particles vibrated back and forth, the wave itself was able to move forward through the medium. So those were parallel motions, and that's why we call this type of wave longitudinal. But there's another kind of wave called transverse, and you can see it here. So what makes that one special is that the vibration of the particles themselves were going, at least in this case, sort of up and down, right? So here's a particle moving up and down, but the wave itself was able to move through the medium from left to right. So since there was a perpendicular difference between the motion of the wave and the vibration of the medium, we're able to call that kind of wave a transverse wave. So one of the things you guys should know is that transverse waves can be really in any direction. So they can be like up and down in a vertical plane or left to right in a horizontal plane, and there's no restriction on that. Longitudinal waves are just compressions, so they don't have that same kind of orientation. All right, we have to discuss frequency on this slide. A frequency is the complete cycle of changes at one point in a medium, or we can call it a cycle. And the number of cycles that happen in a second is called the frequency. So as an example, we could say that a frequency of 1 cycle per second is called 1 hertz. The hertz is the unit for frequency. So if you are standing on a dock and there are waves passing under you, and one wave passes under you every 1 second, then the frequency of those waves is 1 hertz. There are a couple of other ways to represent this, so check this out. You could say 1 Hz for 1 hertz, but it really means cycles per second, and per second means over seconds. So you could also think of that as 1 over seconds. And lastly, if you're super mathematical, you could think of it as s to the negative 1, because when you raise something to the power of negative 1, you're really saying that it is 1 over that value. We would call that a per second. One thing you guys might be familiar with is that frequency, at least in sound waves, is associated with pitch, and frequency in a light wave is associated with color. The human ear can detect frequencies up to 20,000 hertz and as low as 20, and the human eye can see frequencies that are much, much, much higher in terms of light. So let's answer these questions. Which wave characteristic is defined as the number of cycles of a periodic wave occurring per unit time? And of course, that's frequency. Let's do a very simple math question. What's the frequency of a wave that passes 6 cycles every 2 seconds? So since frequency really is the number of cycles per second, and we have 6 cycles passing in 2 seconds, then the frequency here is going to be 3 hertz, which is the same thing as saying 3 cycles per second, which is the same thing as saying 3 per seconds. All right, the 2 units that are used to measure frequency most commonly are hertz and per seconds. All right, there is another characteristic of periodic waves, and that's called period. Period is really the inverse of frequency, so it's related, but it's sort of the opposite thing. Remember that frequency is the number of cycles per second, and period is related. It's the number of seconds in a cycle. They're just opposite things. So I had used a metaphor of you're standing on a dock and you count the number of waves that pass every second. That would be the frequency. But let's say that you're standing on a dock and you are just watching one wave and you're counting how many seconds it takes for that wave to pass through. The number of seconds that it takes for that wave to pass is called period. So they're very related to each other. They're just inverse, and you'll find this equation on your reference table under the waves section. Period is 1 over the frequency. Let's try a very simple question. If the frequency of a sound wave is 440 cycles per second, what would the period be? So noting that they are inverse of each other, what you really need to do is a simple calculation in your calculator that just says 1 over 440 and see what you get. So I got 0.00227 seconds. That's the unit for period. But with scientific notation, I can take this decimal and move it 3 spaces to the right, and I can get 2.27 times 10 to the negative 3 seconds, or choice 1 as my answer. All right, last question on this slide. If the frequency of a sound wave is doubled, what would happen to the period? So again, noting that period is really the inverse of frequency, then if you were to double the frequency, or give it a value of 2f, you would really be making the period only half as much. On this slide, we're going to discuss amplitude, which is the maximum displacement of a vibration or oscillation, but it plays out differently in transverse and longitudinal waves, so I'm going to do a couple of quick sketches to explain all of this. So on a transverse wave, we have these things called crests and troughs, and the amplitude would be measured simply by going from equilibrium to the top of a crest or equilibrium to the bottom of a trough. But in a longitudinal wave, you don't have crests and troughs. Instead, we have compressions, which are the areas of compression for the particles, and rarefactions, which are the areas of anti-compression, the area of spaced out particles. So the amplitude can be measured as the density of these compression lines, so the more closely packed they are, the higher the amplitude. And conversely, for rarefactions, the less compressed these areas are, the higher the amplitude of the wave. Now, for longitudinal waves, we actually can think about amplitude as being like, if it's light, we could think of it as the brightness of the light. And for longitudinal waves, let's say that we're talking about sound here, then we can think of the amplitude of the compressions as being like the volume of the sound. So for sound, amplitude is like volume, and for light wave, amplitude is like the brightness of the light. But I must make one final point, which is that the amplitude of a sound wave is not related to its frequency or pitch. So you can imagine that if there's a very loud sound, it doesn't change the pitch of the sound, it just changes its volume. All right, let's do some waveform diagrams for both transverse and longitudinal waves. When we graph a wave versus time, it's called a waveform. And we were just talking about this on the previous slide, but we have rarefactions here and condensations here, or compressions. And we can measure the amplitude by looking at the density of the condensation or the anti-density of the rarefaction. And when you're looking at this on a transverse wave, you can see that there are like many different ways to represent that wave. And when we look at waves A, which I'm tracing now, and wave B, which I am tracing now, you can see that they have the same wavelength, meaning that each one of these completes a cycle in the same sort of length of time. But waves B and C, which I am tracing B right now, and then here is C, they don't have the same wavelength, but they do have the same amplitude. On this slide, we're going to discuss phase. Phase is defined as 2 points on a waveform that are displaced from their equilibrium by the same amount in the same direction, and they're moving in the same direction. So, for instance, if you take a look at, let's see, point B and point F, these two guys are both displaced from equilibrium by the same amount in the same direction, meaning up, and they're on the same wave, so they're both moving in the same direction. So we're going to call those in phase. Now similarly, points A and E are displaced from equilibrium by the same amount, which is they're not, in the same direction, of course, and they would be moving in the same direction as well. So we have those 2 points, and then we also have C and G. C and G are also displaced by the same amount in the same direction, and they're moving in the same direction. So if you're taking some advanced math this year, you probably know that we use degrees to represent the cycles of a wave, like there are 360 degrees in a wave. And that also means that you have 2 points that are in phase, like B and F, that they are 360 degrees apart, which you can see on this diagram. If you had 2 points which were completely out of phase, such as points C and D, they are displaced by the same amount but in opposite directions. Then you could see that they're actually 180 degrees apart, which is half of a wavelength. So speaking of wavelength, we have a really cool symbol that we use for that, lambda, which sort of looks like an upside down Y. And it's their Greek letter for lowercase l, so that we use it because L for length, so wavelength. The distance between the 3 pairs of points that are equal to 1 wavelength are the same as the 3 we chose for the ones that are in phase, because 2 points that are in phase are a wavelength apart usually. So we're going to go with, let's see, CG, BF, and I think AE. So because wavelength is a length, it's going to be measured in meters or maybe even nanometers. And know that if you have 2 points in a transverse wave and they're 180 degrees out of phase, that's half of a wavelength. And using our cool new symbols, we can write it like this, 1/2 lambda. Or some people would write lambda over 2. The wavelength of a transverse wave is measured between successive crests or troughs, meaning we could measure it like that, between 2 crests, or I don't have 2 troughs in this diagram, but it would be over here, 1 here and 1 all the way over on the left. So just measure the distance between 2 crests and 2 troughs, and you've got a wavelength. If it is a longitudinal wave, you need to measure the distance between successive condensations or rarefactions. And on this slide, I need to discuss the speed of a wave. We're going to use v, and its unit is going to be meters per second. I can explain that now. So the equation is v is f lambda, and we know that the unit for frequency is hertz, but an alternate unit for frequency is the per second, or the 1 over the second. And for lambda, the unit is going to be meters because it's a length, so it's going to be measured in meters. But when you combine these two terms, you're going to get meters per second, which you may remember from way back in the day is the same as speed. So when we are measuring the speed of a wave, multiply the frequency of the wave by its wavelength, and you will get its speed. So not all waves travel at the same speed. One of the things you're probably familiar with is maybe you've seen a baseball game, and you can see the ball be hit, but you won't hear the crack of the bat until much later. The reason for that is because the light bouncing off the ball and the bat is traveling at the speed of light, which is considerably faster than the speed of sound. The speed of light is 3 by 10 to the 8th meters per second. But the speed of sound is only about 346 meters per second in air at like a standard temperature. So that means that there's a huge difference in those speeds, and you're going to see the bat hit the ball long before you hear the bat hit the ball. Okay, math question time. Let's say that you have a wave traveling at 5 by 10 to the 4th meters per second, and its wavelength is 2.5 by 10 to the 1. What is the frequency of the wave? So if v is f lambda, then that means that f is v over lambda. And plugging in values of velocity being 5 by 10 to the 4th meters per second, and the wavelength being 2.5 by 10 to the 1 meters, then we can pretty easily calculate the frequency of the wave. Basically, the way I would do this one is 5 over 2.5 is pretty easily recognized as 2. I'll multiply it by 10 to the something, and the 4 over the 1 is going to be 4 minus 1, so we could do just a 10 to the 3. And this is a frequency, so we're going to use hertz or the per second as our unit. All of our answer choices are in hertz, and my answer choice agrees with choice 2. So this is what we're going to do for our pair up when I see you guys. It has several parts. I guess you can copy the waveform down and the questions, and we'll solve them in class. Leave space between each one of these parts. And also copy down this summary. Of course, I'll need to show you the animation of this wave before you'll be able to identify it. But anyway, that's it for this lesson, and thanks for watching. I hope you learned a lot about Introduction to Waves.